This right here is a genus G surface, and G is always going to be at least 2. So, you know, something that looks like that. And so, great lessons from the work of Thurston, and then the work before him, going back to Dane and Nielsen and Poincaré, geometry, topology, and attention to uniquely flexible. So following amazing theorem. And it's one of these theorems, a lot of math when you first learn about them are, great, and then you get used to it, and they're like, whatever, right? That's just, you should never get bored of this. So the following structures on sigma G are the same thing. And so I'm going to give you 4 different ones. The first is a hyperbolic metric. So we've seen those in lots of the talks. So this is a metric of constant curvature -1. They exist in abundance on surface genus at least 2. Another structure you could put on a surface, conformal structure. So this is it's like a Riemannian metric, but you don't know how to measure distances. You only know how to measure angles. So it's a way to measure angles at every surface between each that vary much metric, right? Would be a Riemann surface structure. This is just a collection of complex plane where the transition and structure of a curve. So smooth. So algebraic curve in some projective space. Okay. In other words, the vanishing loci of a collection of polynomials in projective space happens to be diffeomorphic to sigma G. These are the same thing, and they don't look the same, right? And so let me just remind you of how the equivalences work very quickly. So that different people in the room prefer different ones of these objects right here. To go from A to B, this is just forget lengths, right? That's automatic lengths. Okay, that's one you could do. Let's go from B to C. So you have a structure, and you want to get some kind of Riemann surface structure. So Gauss, constructed. So isothermal coordinates. So i.e. charts. So on on sigma G. So that identify the conformal structure with that on the complex plane. So locally, if you have any structure two-dimensional manifold, locally you can find it, identifies it with the sort of standard Euclidean conformal structure on an open subset of the complex plane. There's a PDE you have to solve. It's called the Beltrami equation. How to solve it, at least for, and now we know how to solve it for almost any data whatsoever. You just need some measurability. So then this gives charts. So with conformal transition functions, right? But basically the ones that define a holomorphic function. So C. So the Cauchy-Riemann equations. I think that's. Say that holomorphic and with an invertible. So biholomorphic with a holomorphic, the same thing as conformal and invertible. So having a derivative just by a complex number, well, multiplication by a complex number, what does that do? It rotates and rescales, right? And so that preserves angles. And conversely, if you have something where the point preserves angles, if you just Riemann equations to see that means it's holomorphic. The derivative is multiplication by a complex number. Okay? That gives us a Riemann surface structure. So if you have the construction of isothermal coordinates tells you that if you have a conformal structure, there's a canonical structure. How do you go from C to A? Well, given a Riemann surface structure, given a Riemann surface S of genus G greater than or equal to 2, so the uniformization theorem implies that the universal cover S is isomorphic to the upper half plane, right? So i.e. that S is isomorphic as a Riemann surface to a quotient of H2 by some group of G, so with G inside the group of biholomorphisms of H2, a discrete subgroup. A discrete, subgroup, right? And now we come to the fact, or the basic fact that you use what Schwarz's lemma or something like that, the group of biholomorphisms is exactly, the group of linear fractional transformations so Z goes to AZ plus also the same the group of hyperbolic isometries. Done. So the unification theorem says here that S is isomorphic to the quotient of the upper half plane by some discrete group of biholomorphic transformations. And those magically are the same thing as, so you get a canonical hyperbolic metric on your. Now the A, B, and C are the same, or at least sort of how you. D is more. So I guess you can go from C to D, or I guess D to C. C is get structure, right? The first examples you learn Riemann surface algebra, C to D is, there's a lot of ways to do it. You can prove it using Riemann rock. If you have a Riemann rock plus some work to show that it actually is isomorphic to an algebraic curve. From an algebraic curve. So these are, kind of very transcendental and confusing operations. They're not obvious identities between these. So for instance, tracing through these, what you see is that if you have structure on a Riemann surface, there is a canonical hyperbolic that realizes. And that goes through a chain of equivalences, right? We start off with a conformal structure, we construct isothermal coordinates, we have formalization. That's not, you can't write formulas. All those are sort of very deep and confusing identifications. Okay, so at every part of has something to say about. They're all saying the same thing in different languages, right? You have algebraic geometry, and they all have things. And there's sort of a lot of beautiful mathematics comes from trying to figure out how to identify the different things. So, what MG is. So definition. So the moduli of GSG curves so G is equal to the above structures. It's the to isomorphism. So the space of isomorphism classes of the above structure surface. So you can imagine deforming any of these structures. If I have, for instance, an algebraic curve structure, this is the vanishing loci coefficients of the polynomials, right? And that changes the algebraic curve structure. If I have a hyperbolic metric, I can deform, well, it's hard to deform a hyperbolic metric. You have a card. If I have a deform comes from you can take some local perturbation of the metric and then just go back to the conformal structure. So these are easy to deform. These are easy to deform. It's a little harder to deform either of these two, but it can be done. Understand the of all such objects. I was supposed to say that, and I took exactly 15 minutes to say that. So look, in math, like no one tells us that we're doing a good job, so we have to tell ourselves we're doing a good job. This is my lesson to the graduate students in the So anyways, how do we construct MG, right? So the construction of MG is a sort of lengthy process. The idea that there would be a space of, say, Riemann surface, that was first dreamed about by Riemann in the 19th century. He even could figure out what showed a complex manifold. It should be 3G minus 3-dimensional. But he didn't actually he didn't construct, didn't even know it existed. But he said, well, if it existed, and he would dreamed it must existed, it at least has this dimension. And so then the sort of story of complex analysis and algebraic geometry of the 20th century is a long story of different constructions that gave more and more structure to it. So I'm probably the earliest construction as a topological space. Yes?
So where do the curves come in?
Oh, okay. So now there's two that are meeting here, right? There's the land algebraic dimensional varieties. Yeah. So those are the same thing. Surfaces to us to just, you go to an algebra conference and they want to draw like, a genus thing. They'll just draw something that looks like that, right? Meaningful to them. And so the intention is to call them curves, but anyway, so I'm going to give you the earliest construction. So, the final construction of this is due to Deline and Mumford in the 70s, the sort of last step of this, who constructed this in such a way that MG is a quasi-projective that's defined over the integers, which is a remarkable thing. So that took a lot of different steps to get it. First, you first construct it as a topological space, then you construct it as a manifold, then you construct it as a complex manifold, then you construct a quasi-projective variety, and then you make it over Z. Like that was a big job. It took 100 years to do it. But I'm going to over Z. So space because it's relevant to its topology. So let's so here is the construction of MG. So what do we consider point S inside M lined up to isomorphism, right? And so then, the above shows that there exists so an injective homomorphism let's call it phi, going from pi 1 of S, which I'm just going to call pi 1, to PSL R. So that right, same thing as the group of, say, hyperbolic isometries of H2. There exists an injective homomorphism with discrete image. Such that S is to of the other upper half plane by the image of phi. So the image of the Sheehan group. Okay? So this is so we now have a construction of them. So every point inside MG can be constructed from one of these representations. Okay, so let's look at the space of all such representations. So I'll call this T sub G. It's usually called Teichmuller space. And I'm honor bound to mention that Teichmuller was a Nazi, so we should not glorify him as a person, but he did. And, you know, he paid the price. He died on the, I think, on the Eastern Front. So what is Teichmuller space? Well, this is the space of, so it's the space of maps from phi, from pi 1 to PSL to R, such that phi is injective, so with discrete image. Okay, so we can look at the space of such representations, injective representations with discrete image. And then, you know, there's big issues here, right? Like pi 1, you know, like S doesn't have a conical base point. So we should quotient by the conjugation action of PS to R. Just quotient by conjugation, it eliminates dependence upon. No. Okay, so this is a nice this is a space, right? This right here, it turns out, so this right here is a subset of just the space of 1 R modulo, now I should put double brackets PSL to R because there's issues with what quotation if you homomorphisms. And so this right here, of course, contained inside, well, you know, so pi 1 has 2G generators, and so we take this as, you know, we take PSL R, we need to know where each of those 2G generators go. So we need G C's, like R, you know, modulo this quotient. So this is a perfectly good topology. So this is from pi 1 to PSL to R, that's just giving, you know, 2G matrices classify one to the relation in the surface group. So this is a perfectly nice subspace of this, and we're taking the quotient. And because of take the naive quotient topology. Okay, it's a nice thing. It turns out that EG is a connected component of the above representation variety. That's not a statement. This is what Teichmuller space is. And so now I want to make the observation. So we have every point in Teichmuller space gives us a point in MG. This fact right here. But it doesn't, but there's many points in Teichmuller space that give us the same point in MG, and that's because we have this word isomorphism from, let's see. So let's see. So we have So a surjective map from Teichmuller space to MG, and what happens, so 2 points have the same image, so if and only if they differ by the action of what's called mod G. This right here is the mapping class group. And there's two different ways to do this. This is the orientation preserving group of the surface modulo isotopy. There's also the same outer automorphism group of pi. So this acts on these spacer representations because the mapping class group acts on pi 1 up to conjugation because of base point, but conjugation, so that doesn't matter. So we have an action, and that gets rid of this arbitrary choice right here. Okay, so this eliminates the arbitrary choice of isomorphism. The choice morphism from S to image of phi. That's what we're quotienting out. Okay. So in other words, i.e., as that mg is equal to tg modulo the mapping class group. So at the topological space. As I said, to turn it eventually into variety defined over Z, but it certainly has a complex structure. It has lots of properties. But if you just care about its topology, this is a strictly construction. Now, I claim that this is analogous to the construction I talked about yesterday. So, is supposed to be, there's an analogy. So between so L sub n, which is x n modulo SL n Z. About this time, I don't expect to remember what this is the moduli space of lattices inside R to the n. We take x sub n, which is this R to the n plus 1 choose 2, 1, right? Modulo the action of this discrete group. And mg, so the care is that, so SL n Z is the role of the mapping class group. So Teichmuller is the role of xn, for that the space intractable, right? That's the following theorem of Fricka and Klein. Well, they showed, with this definition over there, that Teichmuller space is actually isomorphic to R to the 6G minus the G, or inner products of, positive definite inner products, determinant 1, is isomorphic to some Euclidean space. So is Teichmuller space, and it's G minus 6G minus. This is so that this makes the analogy, so mod acts on TG with finite. Okay, so I should, let me give you the picture of why this is true. Okay, so here is the picture. So cut. So G minus 3 curves into 3-hold spheres. i.e. pairs of pants. So, or trousers if you're British. So how does that work? I'll just do it in, there's more than one. Do it in, say, genus 3. Let's say we just take, we could do something like this. Let's add another genus here just to make our lives more interesting. Something like that. If you count, there's 3 times 4, there's 12 minus 9 curves, right? And so every time you need to add 3 more curves to it to make this work. Oh yeah, you're right. There you go. Now I have enough curves. So I have to make a mistake every to make sure that people pay attention. So okay, so we do this now. So now let's talk about these things in terms of hyperbolic metric. So using hyperbolic metric, we can assume the curves are all geodesics. So fixing hyperbolic metric, you can assume that the curves are geodesics. And then the coordinates are then, first, the lengths of the curves of the positive real numbers, and you know the curves, and then you also need to know a gluing parameter inside R for any how these are glued together, and the is the following. The lengths of all the curves. Okay, what would that tell me? Well, this uses the fact that hyperbolic metrics on 3-holed spheres are determined by the lengths of the boundary components. So you need to know, you have a 3-holed sphere like that. You need to know lengths A, B, and C, and once you know those lengths, that determines the hyperbolic metric on the inside of the pair of pants. That's a little bit of hyperbolic trigonometry, basic. And any 3 numbers can occur. So that tells you if you know the lengths of each of these curves, you now know the hyperbolic metric on the interior of each of these complementary pairs of pants, right? And that almost pins it down precisely, but then you have to choose how they're glued together. If you have 2 of these pairs of pants, you have to be able to, when you glue them together, you have to specify how you do that. And if you rotate a bit, that changes how they're glued together. That changes the hyperbolic metric. You might say, well, shouldn't that be a circle's worth of gluing parameters, right? But if you rotate all the way around, then you change the representation. Really a real parameter, circular parameter. Okay, so I just wanted to give this way you see 6G minus 3 come from. They come from the 3G minus 3 lengths of these curves, and then 3G minus 3 glue. So, yeah, sure.
So from the representation point of view, is there a way to sort of get these numbers if I out of the matrix entries, like?
Yeah, so there's things involving traces. Yeah, so at least the length parameters are very easy to write down because the length parameters just come from it's like the translation distance of hyperbolic isometries, right? So you can just write that in terms of traces and stuff. For the gluing parameters, it's more complicated. Yes? No. This is how Fenchel and studied the representation variety. So, but it's much more. What they did was much more complicated. So, any questions? I just like the fact that I don't have to attribute. Everyone attributes this to tech. I like the fact that I figured out that I a little earlier than him. Yes. Because the algebraic geometers can't define Teichmuller space. Because Teichmuller space is a variety. Because so in the land of algebraic geometry, if you have a variety and you pass to a finite cover, it's still a variety. That's called the Riemann existence theorem. It was proven by Grothendieck in this level of generality using resolution of singularities. It was proven by Riemann for curves. But if you have a variety and you pass to an infinite cover, it's almost never a variety. So therefore, like this sort of transcendental thing with Teichmuller just can't do it. They've left and that they can think about. So, any other questions about this? So I'm supposed to take. Yep, I'm working. I am on track. Now that we're on this, so I'm going to talk about the topology of MG. So let me tell you some things about it. So the first thing is that, again, so MG is, it's the quotient of this contracted space by the action of the mapping group, which is with acting with finite stabilizers. And so we see that what we see then is that MG so is a rational K mod G1 or B G, depending on what land of math you live on. And now I owe you a piece of math, right? And so here's a fact. In my first lecture, so I define G as this Gromanian. This is in R, in R the modulo of the diffeomorph is equal to a classifying space for the topological group diff plus of sigma G. This is the Orientonian. Okay? These don't look like the same thing, right? But now I claim that they have the same homotopy type. So what do I mean? What theorem? I guess I'll write it over here. So of Earl and Eels, that says that if you take, this is for G at least 2, this is false for a torus and a sphere, that if you take the orientation preserving diffeomorphisms of sigma G and you take the identity component, identity is contractible. So i.e. the map from the diffeomorphism group sigma G to the mapping class group, right? So we have a projection that gives us a mapping class group is a homotopy equivalent. Right? Take a bunch of contractible things and thing them, right? That's a technical sound, I guess. Washing up contractible pieces and plus right here is homotopy equivalent to a classifying space for the mapping class group. So I didn't give you the correct, these are wildly different spaces. Grassmannian is wildly infinite dimensional, and the moduli space of curves is 6G minus 6 dimensional. They have, issues involving finite groups. They have the homotopy. Okay. They have the homotopy type of the world language. That was a loose end I had to clear up. By the way, how do you construct the map between the two of these? So the map, this is something I've never seen down, but it's a true statement. So in nota bene, so the map the homotopy equivalence, from the Grassmannian of surfaces inside R to the infinity to mg, so that's a submanifold of R to the infinity to sigma g with formal structure. Right? You have a submanifold of R to the infinity. R to the infinity is a natural Riemannian metricon. So you get a Riemannian metric on your surface if you realize it's a submanifold of R to the infinity, and then you just forget the metric and just remember the conformal structure. So proof. I've never seen that written down, but it's a truth. So theoretical, and everyone else model. In any case, though, let me now tell you some things about the topology. So, let's see here. By topology, I really mean cohomology. So, what can we say about the cohomology of Mg? So, remember, cohomology of S, L, and Z is this exterior algebra on these classes Ci. It's a free algebra. That was what Borel proved, right? So, what will the log here be? So, here's a definition. So, they're going to lie inside degree 2i of Mg with, I don't know, let's say rational coefficients. Okay? Maybe I'm going to define them with real coefficients from the a little bit. That's a little bit easier to say all the words you need to say. Work. So, well, we have. So, in 1, this is the moduli space of pairs. So S comma P with P, and P is a point inside S. Okay? It's Riemann surfaces with a point inside them. Okay, so we have a projection from Mg1 to Mg SP to just S, right? We'll call this. And so this is a fiber bundle with fiber the surface. It's actually not a fiber bundle because of singularities, but ignore the it is basically a fiber bundle. Again, there's singularities coming from the fixed points of the action of the mapping class group on type space, but they're okay. That's a fiber bundle. So line of Mg1, this is called the vertical tangent bundle. So what is it? Well, I'm going to do it in the following way. This is the kernel of the map. We're going to take the derivative of pi. It goes from the tangent bundle of Mg1 to the tangent bundle of Mg. Okay? So it's just the, it's tangent vectors that are fibers rather than in the direct. Okay, so this is a 2 bundle. G1, right? We can take characteristics of it. Well, there's not that many characteristic classes of oriented R2 bundles. There's the Euler class. The Euler class of V of G1, that lies inside H2. You can actually make this work integrally as well. And so now I really want classes. I want a class that lies in degree 2i of Mg. I can get classes in higher degrees here by just taking power class. But those are cohomology classes in the wrong space. Right? So a map, this is a weird map. I'll call it this. It's exclamation doing some sort of thing. goes from cohomology of mg1 to cohomology in degree -2 of mg. How do I do this? What I do is, as I'm studying classes in de Rham. So use de Rham cohomology. And then you integrate along the fibers. Right? I can do that. So I have a differential form on my manifold. It's degree of the differential form by 2. And that takes closed forms to closed forms. So this is called way because it goes in the it couldn't possibly respect cup products, right? Well, this is a perfectly well-defined map, and then we can define what these kappa classes are. So these kappa classes, what we're going to do is we're going to push forward. We're going to Euler class of this vertical tangent bundle. And we're going to take the I plus first power of it. That lies in degree 2i plus 2. And pushing it forward, we lose 2 degrees. So that does, in fact, lie in degree 2i of mg with real coefficients. If you're, as I say, if you're a little more careful, find this over. Okay, so we have these classes. And they're very interesting classes. They have what's called the tautological classes. Rita classes. They have very, they sort of show up in geometry in various ways. So for instance, in studying signatures of surface bundles and stuff like that. So symbol them all. So these assemble a ring homomorphism. So it goes from, I guess I'm working with real coefficients. So let's say it's r to the we have kappa 1, kappa 2, a homology ring of mg with real. And so let's call this map tau. It's a ring homomorphism that respects the grading, where you put ki in degree. And so there's an of Madsen and Weiss says that tau is an isomorphism in degrees that are less than or equal to, I think the right number now is 2/3 times g. Okay, so once this is large, as the g is bigger, the homology ring of mg becomes more a polynomial ring in these kappa classes. This is over Q. This is fall. Z is, but you have an answer over Z. Stating it doesn't have a description. So they identify it with in these degrees with the cohomology of a certain infinite loop space, and you can work out what the cohomology of that infinite loop space is. This is what's called stable homology. So, now I want to remind you of something that I told you yesterday. So, yesterday I showed, or I didn't show, I described this. I'll erase that with the wrong. Actually, I'll do this. So, the Borel theorem says that, in the stable range, so the cohomology of gamma with real coefficients of the lattice gamma SLN R. So the stable range means when n is large, independent of the lattice. The question Is there an analog for, MG? So what could this possibly mean? And so that's just saying what that means is sort of a complicated business. So, unlike the class group, or even a discrete subgroup of any interesting topological group. I'll just say Lie group, or any other sort of complicated topological group. It just isn't. So saying it's in. But the one sort of thing that you can do, so one thing that's true is you have a lattice and you have a subgroup of lattice. You might hope that something like that holds for the map. And this is, this is my recent theorem about it. It's some version. And so I'm going to close with a theorem and a conjecture. And I'll say something about conjecture. Let's define for L at least 2, let's define, so we'll call this thing mod GL to be the kernel of the map from the mapping class group to, I'm going to say it's the automorphisms of the first homology group of the surface with, I didn't have enough stuff here. With Z mod L coefficients, I think now I need to have one last piece to close it off. This thing right here, this is, of course, Z2L, or pardon me, Z mod L to the 2G, excuse me. And the automorphism preserved the algebra really SP Z mod L. So these are for the mapping class group, subgroups in kernel of the map from SL SL Z mod L, which I talked about last time. This is myself in, I think I posted the paper in December. It says the following. It says that for G large relative to K, so the map from the cohomology of the whole mapping class group, which is the same thing as the cohomology G with Q coefficients, to the cohomology of, I'll say it like this, to give myself enough room, HK of mod GL with Q coefficients, so is an isomorphism for all L. So we have this sort of analog of the probability theorem, at least in this weak sense, that passing to these find index. Now, let me make some remarks. First, this is false over Z. In fact, there's a long, even for I'll say H lower. That's what I've been doing through this whole talk, but really, homology is a little more natural. There's exotic torsion classes. There's a variety of papers on them by myself, by Bernard Perron, Masatoshi Sato, and others. And they're mysterious. They don't come from algebraic geometry. They come really from these mysterious invariants of three manifolds. So involving the Cup-Brock pairing and the Rock-Linen variant of homology, three spheres and stuff like that. So there are these mysterious torsion classes that seem to have, their geometric interpretation is topological enough. I think the algebraic geometers would very much like there to be some sort of of them, but I only know how to construct them over using three-manifold theory. It's false over Z. Another statement is that it's definitely false outside the stable range. So this is false outside the stable range. So remember, I talked about the cohomology of SLNZ last time. It turns out that there's a theorem that was proved independently by Church, Farb, and myself, and also by Sakasai and Suzuki. This is the same Morita classes. Morita classes. If you take H in the cohomological dimension, the rational cohomological dimension, this should be CD Q of mod G of mod G, let's say with, I think actually, yeah, let's do it with Q coefficients. That's equal to 0. So what was a theorem? Cohomology of SLNZ was 0. Same thing happens here. There's a theorem that was proven by Neil Fullerton and myself that says that, conversely, if you look at the cohomological dimension rationally, mod G of L with Q coefficients is huge. It's exponential in L. It's it's a very large. So this is something, remember I told you, there's always using the style representation of SLNZ to construct cohomology classes near the VCD for SLNZ. And so something similar happens here, though the proofs are much more complicated. So let me see. I have time to make sure. So say that this theorem right here is about these linear congruent subgroups. Now, in Borel's theorem, it's about SLNZ, for instance. All finite index subgroups contain one of these linear congruent subgroups. So Borel's theorem, is about all of SLNZ. There are many more finite index subgroups of the mapping group than just mod GL. Okay, there's a much richer family of subgroups. So, 2 should also hold for subgroups gamma. Is open. But there's been a lot. So for H1, so this is for H1, and during the process section, I'll state my favorite conjecture. People, okay, conjecture. It feels embarrassing to, say something, to use your own name. For H1 to statements about the action of covers of surfaces. So I will state that during the problem session. But there's been a lot of work on that case for H1 involving this conjecture that's sort of equivalent to it. So I think I'll stop there.
Any questions?
Sure.
So you had this action with finite stabilizers.
Right.
This has happened a few times.
Right.
Are there good questions about whether those groups contain like finite index subgroups that act freely?
Oh, they do.
They do.
Yeah, and the way you can see is the following. So the stabilizer is always a finite group. So the question is does there exist torsion-free finite index subgroups, right?
Yeah. Yeah.
That's right. Yeah. And so these ones actually. So for L, these are torsion-free.
Mm-hmm. Okay. So
yeah. So and that's true for SL and Z. That's also true for L at least 3. These are torsion-free. So these always contain torsion-free finite index subgroups, which is that's a reason that this is sort of a very mild problem, right?
Okay.
So.